Okay, welcome back. I'm checking in on our audio and video. It seems like I am live and I am streaming. Here we go, off and running. All right, so I went through homework 1 and I provided some feedback and comments where I thought it might help. But I wanted to go through some of the questions that maybe they came up for you, or maybe you kind of did something, didn't really think about it any deeper, and kind of go through some of the spots where I saw like, all right, maybe we need a little more explanation here, or a little bit of troubleshooting in this part. So I'm gonna pop open this. So I'm in NanoHub. I'm going into that notebook number 1, the reading number 1, or not reading number 1, module 1, homework 1. There we go. Now I'm up and running. I'm in Python. Let me just restart. And so when you restart the kernel, then when you run a cell, so I'm holding shift, hitting enter, then it imports all this stuff at the top. Importing is, so these functions of like import, that's probably why Python is so powerful, because there's so many different libraries and connections. It ends up being like a glue language between a lot of other softwares where people might write finite element code, but there's a Python development kit where you can import all the code that you need to run finite element software. Or even like if you're doing like web development and stuff, you can import all the files that you need to like build a website and then run some Python code and then have like automatically updated websites and stuff. So in this class, like we're trying to understand numerical methods, so sometimes it makes sense to like build something ourselves. And I'm gonna skip around a little bit, sorry to scroll back and forth, but as I'm saying this, like this is an example where there are better linear interpolation methods, but and you know, ones that don't have typos, right? Linear interpolation, like that. So, but in this case, what I'm really trying to do is understand like how does Python work, and if I was looking at linear interpolation methods, like what's the core part of it. And the main thing that if I'm going to do linear interpolation, I need to calculate slope, and then I need to use like some way of using that slope to like get in between the two values. There's even a function called Python interpreter, NumPy interp. And this is even better than the interpolation function that we're creating here, because this will interpolate in between lots of different points. I can give it a whole set of coordinates and then interpolate between those, and I can choose what type of interpolation I want to use. Let's see, period, left, right, none, period, none. But anyway, it does a piecewise linear interpolation, but I think there's also even another interpolation that does, well, you can do like periodic interpolation, but see how it's like taking these 2 points and moving along the way. But anyway, so sometimes we're going to build our own functions, and that's really up to you, like based on the question. In this question, what we're trying to demonstrate is that we know how to identify an error and we know how to fix the error. So in this case, if I try to run this, and most people got like, they were able to kind of see what the problem was here. So let's just plug in 0, 0, and then we'll say 10 and 5. So at this point 2, I should get a 1 because I'm starting at the point x equals 0, y equals 0. I'm going up to x equals 10, y is 5, so a slope of 1/2. But that's not what I get. I get this index error that the index list is out of range. And so when I look at the line where it's telling me, and the way that I like to read Python errors is kind of working my way backwards of like, okay, I know there's an index error. Where's the index error? It happens on line 7. And that happened because I tried to call linInterp. And that makes sense because I only ran one line there, but sometimes there's multiple lines. Like I might have had like a setup, right? I might have said like x equals 2. P1 is this. P2 is that. And then I can say x, P1, P2. And it's still going to tell me like, hey, this is where the error occurred because it was trying to run it here. And I'm diving a little bit deeper. Most people figured out probably before you even ran this function what the problem was, but it's really helpful to dive into why, to tracing this error through the case. So I know there's a problem here, and it's because P2, like there is no P2. So let's do this. I'm gonna move that down. And if I try to run P2, I get that same index error. So let's look at P1. P1 is 5, which is that second value. And then P0 is that first value. So the problem is I'm asking for the second value, but I'm not using base 1 indexing. And again, I'm not telling you anything you didn't know, but this comes up. This happens all the time in much bigger code sources, and it might even happen in like someone gives you some Python code to run at work and it works 90% of the time, but then you start getting index errors 10% of the time. You're like, all right, let me go trace back, like why is this happening? Usually it's off by 1 kind of errors. So I'm just gonna change that line because that's the only place the error came up. But now the error moves down to here. So it's still happening because I'm calling linInterp, and now it's happening in that return statement, but it's still an index error. And again, most of you noticed that. Like if you couldn't call P2 to here, you can't call P1 to there. So change the 1 to change the 2 to a 1, 1 to a 0. And now I get the actual value that I wanted. And so I did a little bit of a deeper dive onto that and like tracing errors. And it's nice when it's a small piece of code like this where we can trace it back. It gets harder when we're trying to figure out like, all right, well, how do I trace the error through these like NumPy functions and stuff? But usually it comes down to something like index error when you try to do this. Maybe it's off by 1, something like that. All right, so that was the first thing that I noticed was like tracking your errors. And like trying to do like a problem solving method. And this is a nice way of doing that. It's kind of like back and forth, try it a couple of times. And that's why I like Jupyter in general, because you can kind of run something, change it, run it again, see what happens. I guess one thing that I was doing that you might not have even noticed, let me run that, run this. So I get an error. I'm like, oh no, I get an error. Let me fix it. 1, 0, and then run it again. And I still get the error because according to this, it's still P12, P11, even though I changed it to P11, P10. And I've brought this up before as we were talking about like Python and Jupyter. I didn't run, if I make an edit but I don't run it, then that edit has not been like saved into my variable namespace. So this linInterp is still whatever input 13 it was, even though I ran it again down here. So this is input 15. So I need to rerun it. So now that's a 16. Now I can run this. Now that's a 17. So 16, then 17. And again, it's something, sometimes it's helpful to be able to like leave names the way they are and edit the code and see what happens as you're running things out of order. Sometimes it's frustrating because you're like, I made the edits, why is it not changing? And if you're ever having trouble, you can always click this kernel restart run all, and it'll go from top and run down the page and run each one individually. So restart run all cells, and now everything that, as long as it doesn't hit an error. So if I still had an error here, then it would stop and it wouldn't keep running things below. All right, so there's that. Then the other part was we talked a little bit about this FizzBuzz example where, and it seems like some people were using this as a case of like, all right, well let me try asking our learning coach for some help on this, and let's see what happens. But I saw some people getting different results because some people had an if statement. So yeah, it's not exactly what I had seen. All right, so I'll write out what I had seen. So we'll say like out is an empty string like this, and then not that. I want to go down here. If, and we'll say n is 30. So 30 should be divisible by 3, 2, and 5. If n percent 3 is 0, out plus equal computational. If n percent 2 equal 0, out plus equal mechanics, and then if n percent 5 equal 0, out plus equal rocks. And let's just try that. And then we'll say print OUT. And so what some people noticed was like, oh no, like sometimes it doesn't put spaces in between these. So instead, what I could do is, I think I can do that. No, it doesn't like that one. So then I saw this other piece of code of like if out plus equal a space. And I think that was run on each of them. Yeah. And that one, I hadn't seen that one before, so I wanted to take a look at that. So if out, so if out is an empty string, it's false. But if out is not an empty string, it's true. That's what I was trying to figure out here. So I saw this come up in a couple of people's different codes. So I wanted to try it out here and see what this was doing. But what we're saying here is that this variable out, if there's anything in here, anything, then it's going to, then this statement is true. So it's going to add a space, and this could have been anything, right? We can make it a smiley face. And it's going to add that to the original thing. And then also I added this print out exists so that I can see like when is this happening? But if out does not exist, if it's an empty string, then out does, it still prints it because out is an empty string, but this is a false statement. So that's what it's trying to figure out. So what we're doing here is creating an output that is initially empty and then adding things to that output. So the example that our learning coach gave us, it's checking every one of these cases. So if it's divisible by 3 and 2, print this. If it's divisible by 3 and 5, print that. So it's going through each iteration of those cases. But this one, when we write it out this way, we're checking each one for every n. So it's not an if-elif statement, because this one is going to check whether or not this is true, even if any of these above them are false. So it's always going to check them. That's what that if means. So now let's try something else, because there should be else out equals, oh yeah, this one should be over there. So in this case, yep, and what I'm doing here is saying if this is true, then add that computational, then add the mechanics, then add the rocks, else out is just whatever that integer is. So let's throw in 7, because 7's not divisible by 2, 3, or 5, and see what happens. And I get 7. All right, cool. So now let's see what happens if it's 13. Still works. So now we'll take this whole thing, bump it over. So I created something that seems to work for n in range 0, or well, yeah, let's do 0 to 30. So at 0, it's divisible by all 3. I mean, technically. 5 works, then 10 is 5 and 2, so mechanics and rocks, 15 computational rocks, but 16 is divisible by 2, but it's not. It should give us mechanics, right? So something's weird there. All right, 18 also, actually even 2 and 4 are not working right now. And why is that one happening? Yeah, 2 doesn't work, 3 doesn't work. So we're missing a few things. This was a different problem than I thought would come up, but because I was expecting this part. Oh, yeah. All right, so that's what's happening. So it only works if multiples. All right, so because this is a new if statement, and when this is not true, it's going to rewrite our out as that integer. So the only times this is working is when this statement is true and it's adding that rocks to our string. And that's what we see here, is that really it's only happening on the 5s. The 25, 20, and so let's get rid of that. All right, so then that thing's not working. Try this, and then we just get blanks. Like it is working, but it's not printing out those numbers. It's like, so maybe I just need like n comma out, and now it's getting better. Like we are printing out n, but we're printing out n every time. And so one nice way to format this would be, we could have a tab in here. /t is tab, and now it'll like, so the left hand side is our index and the right hand side is our output. All right, we're getting closer. So what I could do is add, not that. I could add an elif here, something like that. Or I could have this case of like if n%3 and is not equal to 0 and n%2 is not equal to 0 and n%5 is not equal to 0, out equals string of n. And now it's getting to the point where it's more what we wanted, where a 1 is a 1, a 7 is a 7, and the rest of them are filling up. So all these prime numbers, I mean, they're not prime forever, but at least in these first like 30 examples. Let's go to 31 so we can look at it. So 31, we get that comp mech rocks, and then all these other ones seem to be working a little bit well. But yeah, this is kind of like my troubleshooting. And I saw some people use like ==1, but let's take a look at, let me make like a new line here. For n in range of 11, just go 0 to 11, print n%5, and then we'll print n and n%5. So 0 divided by 5 is 0, remainder 0. 1 divided by 5 is 5, remainder 5 is 1, remainder 4, and then it's 2, and let's do one more. So n//5 like that. And yeah, so you can use this percent and this / to figure out like remainders, or like so we want this one. So 1 divided by 5 is 0, remainder 1, so 1/5. 2 divided by 5 is 0, remainder 2, 2/5. Meanwhile, 5 is 1, remainder 0. And then 6 divided by 5 is 1, remainder 1, so 1 plus 1/5. And then we get up to 2. And these are the two kind of math operators for getting like the division, like what is the whole number division, and then what is like floor. So this is kind of our floor division, like get an integer out of that division, and then this one tells us like that remainder. So it's not always, let's go up to 21. This %5 can go from 0 to 4. And if it was a %7, it can go from 0 to 6. And that's because it's always like the remainder value in a long division operation. So you can use the not equal to say like, all right, if there's any remainder, then it's not divisible by it, or you would have to factor in, you'd have to say like, oh, it could be 1 or, for 2 it's 1, for 3 1 or 2, and for 5 1 2 3 4. Yeah, so that was just something that I noticed because I saw like if it's equal 1, that's only a special case because it only happens for 1, for, well, that one's, it only happens for 1 and 6 and 11, 16, it's always like 5 times something plus 1. That's when you get a 1 there. And yeah, so this one works. If you want to use those like if statements, if you want to force Python to check every if statement that you can. I don't know that it's necessarily like faster to use elif statements. In general, like it helps to speed up your code to use elif, because logical operations are like things that take the computer time to like stop and check. But we're probably not going to see a difference here. Most of our time is being spent printing our outputs anyway, so 6 of one, half dozen the other. Cool. Then I was really impressed with a lot of the work that I saw. Seems like you're doing a great job taking the reading and using resources that you have, maybe previous videos or other places, and being able to do this, because I saw really good work here. The main thing that that it's easy to forget is just this, I didn't want to do a shift enter. I wanted to do 1 2 3, make a doc string just like this. So this function takes in an array x and outputs sign of x and cosine of x. And this is actually something that AI is pretty good at. So sine x equals np dot sine of x, cosine x equals np dot cosine of x. So let's grab this. I need you to add a doc string to this function I wrote for sine and cosine evaluation. I'm going to remove this. I'm going to remove my doc string and just have AI write one. Wait, what? Oh my god, it's still trying to give me, here, let's make a new one. Just make a new topic. It was getting stuck onto the FizzBuzz example. It just loves FizzBuzz. So let's see what calculate sine and cosine of a given input. X is float or array-like. And this is pretty good. Not a bad doc string. So I could take that, paste it in here. Only thing that I would add is where the tuple is composed of two arrays, sine x, cosine x. And this is a great way to help you kind of think about and document your code. So if you have something, and a lot of times like you need functions to run, you need them to be kind of simple. Doc strings are so much better than like just putting little comments in your code, like typing things in there, because they're a lot more accessible. Because now I can, well, if I could actually get some code that runs, what's the problem? Let's try that. All right, so what I just did there is, you probably haven't had to deal with that before, is tabs and spaces look exactly the same, but they're different in Python. For I in range 0 to 5, print hello, 1, 2, 3, 4, print world. All right, so in the first case, I have 4, let's see. Oh, okay. So default in Jupyter is that it is a tab. So let's grab, which is good. Well, a tab is just actual 4 spaces rather than a real tab. So let me grab, this thing was an actual tab. Control C. paste it in here. Ugh. There we go. I'm trying to find this tab. They're invisible is the problem. Anyway, so tabs and spaces, they look the same, but they are different, and Python can't. If you're mixing them, then it becomes a problem. If you're working in Jupyter and you're typing things yourself, so you're hitting tab, each tab is just 4 spaces. I think you can change that if you want, but I would not bother with it because it'll just add headaches to it. But that's what was happening here, is that this was a tab, meanwhile this was spaces, and it didn't like that copy paste action. So if you're copying things over and getting weird errors like that, like the spacing doesn't match, that might be why. Okay, so now that was an aside. I have that. Everything that I write inside that doc string is available inside this help file, and the help file tells me where it came from, tells me what it returned, whatever I wrote, that's what it's going to tell me. So if my doc string just says this is a function, then I need to go find, then I have to go like figure out like, all right, well, where did I write this? Okay, it was an input inside this module. Like, oh my God, where's this thing? So it's always very helpful to like actually run it. Okay, next thing that came up is like timing things. This is something, so being able to time computer code is a really helpful skill. A lot of times we don't, as mechanical engineers, we don't really care how long it takes the computer to run. There are times where things are going to take a really long time, and we have to figure out like what the bottlenecks are. Usually that's outside the scope of where we're at, like trying to design like solutions to numerical methods, because we're more concerned with like, did it converge? Are the answers precise, or are they accurate, or is there any other weird things going on? But timing is a really helpful skill, and the main thing that you want to time is apples to apples. Like, you don't want to add extra stuff to that timing thing. So let's take a look. Coming in here, I'm gonna do some fancy list comprehension for my A99 creation bracket. So I create 2 lists, one inside the other. I'm gonna say I times j. Inside this, I'll say for I in range of 10. And then inside the next list, I'll say for j in range 10. I saw maybe a few examples of this, but this is a very like Python way of doing things. Not many programming languages let you throw for loops inside of lists, so you can like create something on the fly like that. And it's a cool way to do things, and it makes it, rather than having like nested for loops where you're like populating this thing, populates it on the fly. So I run that, and let's double check that it's giving me what I want. And sure enough, I get a row of zeros, a column of zeros, and then a row of my 1 times 0 to 9, then 2 times 0 to 9, and the same thing in the columns. We have like some symmetry because it's a multiplication table. All right, cool. And really, like, this is the main thing that's changing. Like, whether I take the mean and standard deviation inside this cell or I do it at some other point, the main thing that changes is like if I'm using for loops versus using arrays, what is the difference in how long it takes to run that code? So let's try that. So I'll time it with just the creation of A99. It's gonna run it, I think 1,000 times by default. No, 100,000 loops. So it took 6.5 microseconds to do that. So now I'm gonna create this. Oop, sorry, I don't mean to keep jumping up and down. And I'm just going to time so I'm creating A99 with a for loop versus creating A99 by just doing that math. So this was 6.5 microseconds. This was 512 nanoseconds. That's a big difference. And the more stuff I add to these time it scripts, the less of a difference I'm gonna see, because now it's getting swamped by other stuff. So if I also say like, okay, we'll take the mean of A99, also take the standard deviation of A99, and I'll do that down here too. So it's still apples, like I'm still comparing the same two operations. But now the things that are taking more time are just calculating that mean, calculating the standard deviation, and whether it's an array or a list of lists, like these operations are turning them into arrays anyway. And then if I start adding even more to this too, like if I also say like import matplotlib dot pyplot as plt, and if I do that here, then I have to do it up here, because I want to compare the same thing. So if I'm also running an import command, now there's going to be, well, I guess it's still faster, but I think because I had already imported it, so it just barely took any time. But importing commands, you don't want to like time those import commands unless you care about how long it takes to import something. Like maybe you changed a function and you think it's going to take longer, but we're not doing that. We're not like creating our own libraries of functions. So the main thing that we want to do is get rid of all this extra noise, because we don't want to time all this stuff. We just want to see what's the difference between arrays and lists, and that's what we want to do. So 6.6 microseconds, it's going to change every time, right? And then half a microsecond, so much faster to do it with multiply two arrays versus like multiply two numbers and save them into different lists of lists. That's the main thing that we're trying to do here. That was just one thing that I noticed about timing, about trying to use the timer, and it came up again in this exponential Taylor, where we're also using that timer to run this. And yeah, let's run that. Let's try it. % time it for exp, since we're on the topic, right? Of 1 and 2, and then I'll copy paste 1 and 10. And you know what? Why not? I saw a few people do this where they also said like, all right, well, let me see if there's a trend here. So plt.plot of my x-axis is 2, 10, 100. My y-axis is 0.491, 2.49, and 82.9. So taking this, because my independent variable that I'm doing here is looking at what is the truncation error in this Taylor series. So the smaller I make those numbers, then the quicker it runs quicker. But I want to know what's the payoff, like, because we're comparing like how fast it takes to do the calculation versus how accurate is it. That's kind of the balance that we're doing here. So I'm taking the time in microseconds and the order and the number of things that I did, and looks okay, right? I'm gonna put it as like square dots so we can see that. Plotting, okay. Let's look at maybe log. It's weird. I don't know why it's taking so long. There we go. All right, so now I'm starting to see like seems a little straighter on that log plot. So as I went from 10 to 100, it went from 10 to the whatever 0.5 to 10 to the 2. And that seems to be, so a factor of 10 resulted in that factor of 80 or 40. So it was like 40 times longer for every factor of 10. That's kind of what I'm seeing from this log plot. So I could just, I saw some people use this like lin interp and just take these last two values, right? I'm just gonna copy them down. $100,000, right? Yeah. And then my first input is 2.49. My second input is 82.9. And then I get this result that it should take 89 seconds if I just use, like, I'm saying interp, but really this is extrapolation. Like our method that we created is interpolation and extrapolation. So this is one way to do it. It's, yep. And if I want, I could say over 1,089 seconds. I like. I'm being lazy here. Really, I would save this as a extrapolated thing, and then, but 89.3334 seconds. All right, so now last thing that I wanted to talk about was thinking about Euler integration, because a few people kind of pointed out like, hey, I don't know what Euler integration is, and that's a great like point to hone in on. Is like, where is this coming from? Why are we using this here? So let's take a look at what Euler integration actually is. So I'm gonna open up this thing. I'm gonna grab this. So really what I'm saying is that the population is K, the change in the population is K times the current population. And for Euler integration, it doesn't have to be a simple kind of first order differential equation. It can be all sorts of stuff. And in this case, it's always like the amount the population grows is proportional to the population. And that's a nice simple model that like the more people you have, the more babies they will have. And this K term is the main governor. So some people will pass away, other people will be born, and overall K is like some number there. So it's the simplest like population growth here. So Euler integration the idea is that there is a function of population that solves this. We already know what it is. We know that it's an e to the k times t kind of function, but sometimes we don't know what it is. Like this might be dp dt is k times p to the n plus the sine of the population, like something weird like that. And it doesn't really matter for Euler integration. It really does not matter what the function is. You can plug in any differential equation and we're going to be able to like step forward in time. So if p of t exists, like there is a solution that is p of t, I can expand it as a Taylor series. So p of t is p at 0 plus dp dt times delta t plus d squared p over dt squared times delta t squared over 2 factorial plus, and I can keep going from there, a whole bunch of higher order terms. In our Euler approximation, we're just saying like, all right, this is close enough that if I know population at a given time, I can use the slope at that time and step forward. So in our case, we have like population at 1900 is here, and because I know the population there, that's our 0.013. I can take a step forward into 1920 right there. And then from here, I can say like, all right, well now I have a new population that's bigger, and I'm gonna take that, well really this should be k times that. Because this one is bigger, this slope is going to be 0.013 times that p of 1920. So the slope will keep increasing because p keeps increasing. And that's what this dp dt is, k times p. And that's what we're trying to do with, because once we have that relation, we can create a loop to kind of go through all those populations. So let's say P 1900 is that pop of 0, that first population. Oh, and I'm gonna say, I like to set time first. So time is a range 1900 to 2021, step sizes of 20. And do I want, let's do I. And we'll say P Euler is NP dot zeros of len of t. So I'm doing a couple of steps here. I set up, time is always an independent variable. Whether I know the function or I'm trying to solve for the function, I can always say, all right, show me the answer at these points in time. And that's what I'm doing here, saying like, all right, start at 1900, go to 2020, and this is up to but not including, so I said go to 2021 and take step sizes of 20. So start, stop, step is the general kind of A range input. There's also linspace, which is start, stop, number of steps, and I could do that if I want. This is the P1900 is that population at time 0. So I'll say this P Euler of 0 is P1900. So I'm setting my initial population to something that I know already. And for every differential equation like this, they're called initial value problems. You need the initial value, otherwise there's no way to solve from there. So now I'll say P of Euler, and in this case I'll go I. So when I is 1, this will be a 1, and that population is going to be population of I minus 1 plus K times population of I minus 1. And then the main thing that sometimes I forget it too is this like time step. I didn't even define it yet, right? So let's say I'll call it dt, and then up here I'll say dt. So dt is 20. Just kind of rearranging as I'm thinking my way through it. And that's taking this like weird concept of a Taylor series expansion and turning it into like real actionable code. Like, how do we actually solve this? And now I can say, oh, K is not defined. So let's define it. K is 0.013. And then I see this curve. It always helps to compare it to something, right? Year, POP, do some squares. So this was the actual world populations. It should line up exactly this first dot, no matter how converged this thing is, it should be exactly the same. And I could change it, make it solutions every 2 years, right? And then things change a little bit, like it's getting closer to those. I can make it every year, and it's still getting a little closer. But main thing was I wanted to kind of dive into like where is this coming from? Like why are we using a for loop to solve a differential equation? And it's the Euler approximation is like the default method for integration, numerical integration. We'll look at some different ones, and there are way better integration methods than Euler, but it gets the point across of like how does this work? And that question of like the idea of like truncation error and round off error. This is the example of truncation error, of like we can reduce truncation error by decreasing that time step, so we can make the function closer and closer to the actual p of t that we're looking for, but we'll always have some truncation error because we're cutting off that function p of t and just saying it's linear for every time step. All right, cool. Keep up the great work. I'm looking forward to seeing revisions and also seeing like how people interact with the learning coach and how the learning quizzes go for as you take these like reading quizzes. Yeah, so looking forward to it, and I'll see you next time.